So this is the first lecture on the content from Chapter 9 of the Callister textbook. And this chapter deals with phase diagrams. So these phase diagrams are, well, made of phases. And we should define what that is. So a phase is a region of space, and within that region, all of the physical properties of a material are uniform. Or, I don't know if uniform is the right word, perhaps the same is a better way of putting it. So a phase diagram is a way that we're looking at the existence of phases in a material system. And these phases, they'll change from one phase to the next as you change external parameters. For example, changing a temperature and changing the pressure. But they also change as you change the components present in the system. So a component is either an element or a compound. And these elements and compounds are what constitutes the material system. So there's a material system that you put different components in, and then based on thermodynamics, they establish a certain set of phases that make up the microstructure. So a simple example of a phase diagram would be a phase diagram in which we have on one side water, the other side sugar, and the y-axis is going to be temperature, and then within this mixture, let's say that we call this the percent sugar. So within this, on the far left, at this point we have all pure water and it changes the temperature. This side is pure sugar and it changes the temperature. And then here we'll have, say, 20, 40, 60, 80 percentages. So it's percentage of sugar. So anything along this line would have 80% sugar and 20% water, because we're saying that in our system it is all water and all sugar. And then we have temperatures, say 50, 100, 200, 250, and those would be in units of Kelvin or what have you. And then we have phases. So for example, if we start off here with pure water and we start to put in some sugar, you know that sugar becomes a solution. So it goes into solution with water. And so in this region here we have a liquid, and that liquid is a solution. But as we keep going over here, at some point we reach the solubility limit where we can't put any more sugar in. And as we add more sugar, it changes. And over here we have liquid plus solid sugar. on this side. And the point where that difference comes about, that is our solubility limit. And in fact, we can draw an entire line that does something like this. OLU. So everywhere on the left-hand side it's pure liquid, and on the right-hand side it's liquid plus solid sugar. So this liquid is the phase. And here we have two phases. We have a phase of liquid and a phase of solid sugar. And here at this far edge, it's 100% pure sugar, which means there's no liquid. So here is again a single component phase, which is pure sugar. And notice that this curve has a shape to it, and we know that the warmer you make this liquid, the higher the solubility. Right? So this is a phase boundary here that separates these two regions of our phase diagram. So yeah, that example is a pretty good example of a phase diagram. In materials, examples of components we can have, again, alloys, we can have elements. So for example, we can have zirconium, copper, nickel, iron, carbon, ... But we can also have stoichiometric compounds. For example, Al2O3, alumina. Sodium sulfide. Silicon sulfide. ... And those will be our components. Our phases, well, we can have the phase that we had before, liquid and solid and vapor, right? Solid, vapor, and those are certainly valid phases, but more importantly, we know that there's more than one way to make a solid. Right? You can have different crystal structures. Right? So for example, iron and carbon, they make a solid solution, and they can take an FCC crystal structure. So we have an FCC phase, or we can have a BCC phase. And in our phase diagram, we'll then be able to show the phase boundaries as a function of, say, temperature and pressure, or composition and temperature, or composition and pressure. And that's what a phase diagram is. It is basically a map showing you the relationship between the phases and the composition, the amount of each component present, and then the temperature, pressure, and other thermodynamic parameters. Now, once you have these phases, the phases come together in the system and they make up a microstructure. Solid phases. So it's something that oftentimes you'll hear people talking about, things like the eutectic microstructure. And the eutectic microstructure is made up of two phases. So we can classify microstructures also by their given names and their given characteristic structures. But there's a distinct difference between a microstructure and a phase. So talking about phase diagrams, they denote systems that are in phase equilibrium, or a thermodynamic equilibrium. Right, so they show phase equilibrium. And this is important because this phase equilibrium, this is something that you can address using thermodynamics, and it's something that is addressed using theory. So we spent a lot of time learning about the free energies and the Gibbs free energy for different phases under different conditions, and from that we develop phase diagrams. Now, these phase diagrams are in equilibrium, but most of the materials that we know and love are not in equilibrium. Useful materials, let's call them. Are not in equilibrium. In fact, they're metastable. And basically, what we want to do is we want to use phase diagrams to identify the phases that we're interested in putting into our microstructure, and then we want to devise processing methods that allow us to create a microstructure with the phases we want, and then we want to quench that in order to freeze in that microstructure into a metastable state. And we say it's metastable, meaning that it can transform from that into its ground state, which is the low energy structure. But really, it's not going to. And the reason it can be stuck in this metastable state, and the reason that we can use this to make engineering materials is because it's metastable, but it is kinetically limited. Right? So basically, what's happening is that in order for one microstructure with a set of phases to transform into another, there has to be this mass transfer where atoms move around and rearrange themselves. And that requires, we know it requires thermal energy, right? Because we know that for diffusion to occur, you have this energy barrier that you have to overcome. And to overcome that energy barrier, it's not going to happen, at least not happen rapidly, when you're sitting at room temperature. So, limited mass transport. Or diffusion. So let's look at one simple phase diagram. So, and this is simple one component phase diagram. And let's have our component be water. So one component water, and we're going to plot pressure versus temperature. So let's change colors here. We know at low temperature we have a solid water, ice, and over here at high temperature, we have liquid vapor, and in the middle we have liquid. So solid, liquid, vapor. And the phase boundaries look something like this. So if we now have, say, some given pressure, and we start out and it's a solid, as we increase the temperature, at some point we reach this boundary and it melts. And then becomes liquid, and if I were clever enough to have drawn my line all the way out, and here we reach a point where it vaporizes. And now it is vapor. And that's how we read a phase diagram, right? And conversely, we start out as a vapor, and we come here. At this point, it condenses from vapor into liquid. And then continuing back, is liquid, liquid, liquid. Some point here, it freezes or solidifies. And now it's a solid. And this behaves the way we know water will. Now, you look down here, if we start out solid in this region, at a lower pressure, at some point it goes from a solid straight to a vapor. So what's happening here is sublimation. So it's skipping the liquid phase. This point is called a triple point. At the triple point, if you're able to hold your system right at that exact pressure and at that exact temperature, if you look at the system, then you'll see both, all solid, liquid, and vapor coexisting at that point. In a similar fashion, if you can pick a pressure and temperature such that you're right on one of these phase boundaries, you'd see liquid and vapor coexisting. So anywhere you have one of these lines that separates these phase regions, if you can create a system that sits right on that, then you're going to have coexistence of these phases. So this is a simple one-component phase diagram. So now let's go to kind of the next level of complexity, and we'll go to a binary phase diagram. Now in a binary phase diagram, we still have temperature and we have pressure, and now we have the mole fraction of what I'm going to call component A and B. So these are what control our system. Now, of course, kind of the nice thing here is that XB is equal to 1 minus XA, right? So we only have these three parameters that we can control. Now, really that means we need to have a three-dimensional map. But in order for us to represent this on paper, what we'll typically do is we'll pick either temperature or pressure to hold constant, and as a matter of what's useful, because it's pretty simple for us to use an oven or a furnace to control the temperature, we'll hold pressure constant and for some particular constant value of pressure, we will plot the temperature and then the fraction of A or the fraction of B. And we're going to begin with the simplest binary phase diagram. And this involves binary isomorphs. So an isomorph, these are two components that have the same crystal structure and they have similar size. And as a result of having similar size, that means that they form they're completely soluble in each other. So let me show you what that entails. So this is what a binary isomorph phase diagram is going to look like. So this is going to be fraction of, say, B. So this is A, this is B, and this is temperature. At high temperature, at a high enough temperature, we know we have a liquid. At low enough temperature, we have a solid. And this solid, we know that it is a solid solution. Because we're saying that our A and B are isomorphic, so they have they're completely soluble in each other. And we denote solid solutions using Greek letters. So this would be the alpha phase, so to speak. So we're going to call this alpha. And then somewhere between these two, we're going to have something like this. Gives us alpha plus liquid. So we get alpha, we get liquid, and then alpha plus liquid region. So this is something that is important to know about binary phase diagrams. If you have a binary phase diagram and you have a region of space with a single phase and you have another region of space with a single phase, in order for these two to come together, there must be a region between them that has the two phases. And this is just universally true for binary phase diagrams. So something else that's worth noting here is I did this as mole fraction, or percent of A. When you look up phase diagrams in books or in papers, it can be mole percent, or it can also be weight percent. Right? Weight percent A. Well, mole percent A. And these two are not exactly the same. You can convert between the two if you have the atomic mass, but you can't directly read the weight off of a mole fraction phase diagram. And just as we discussed, must have chapter 2 or chapter 3, mole fraction is really handy if you're talking about chemistry and you're thinking about the chemistry of what's happening. Weight percent is a lot more handy if you're actually in production and you're making something and you want to know how much of A and how much of B am I putting into my system. But the important thing here is that whenever you work on a problem, or whenever you're at your place of employment and you're looking up a phase diagram because you have a new batch of material coming in, make sure that you check whether you're dealing with mole percent or weight percent. So this is our phase diagram, and we can think of it again just the way it was before, right? If we start up here at some composition, and we're at high enough temperature, we have liquid, great. Come down here. At this point, we cross what's called the liquidus line, L-I-Q. And that liquidus line is the separation between being all liquid and first starting to form a solid. And in this region, now we have some solid and some liquid. Keep going, still have solid and liquid. And at some point, we touch this line. This line is called the solidus. Yes. The solidus line is the place where your liquid disappears, and now we've got all solid. And that's how you can read from a phase diagram and know what phases are present. But now what we want to do is we want to talk about how to read quantitatively from this, and in particular we want to be able to determine the composition of the phases and the amount of each phase, right? So is green visible here? Yeah, okay. So let's say that we're right here. Right, we just crossed the liquidus. Well, that means that we are mostly liquid and a little bit of solid. So what we do is we draw what's called a tie line. And that is a horizontal line. And that horizontal line will touch the solidus and the liquidus, and then we have where it touches our composition line, and that subdivides our tie line into two parts. If we want to talk about the composition, the liquid phase, which is on this side, so it's on the liquidus, right? It's right next to that point. If we drop a vertical line down to there, that gives us the composition of the liquid. So let's call this XB liquid. And then over here, where the tie line touches the solidus, we can drop a horizontal line down, and that gives us the composition of the alpha, or the solid phase. Great. So we have the ability to read the composition. The kind of interesting thing is that as we cool, for example, say we come down to this point, well, now if we draw our tie lines in, compositions have changed. This is XB alpha, and that is XB liquid. So as we cool our system through this two-phase region, the composition of the alpha and the composition of the liquid change. So that's one thing that we can do with this type of phase diagram. Another thing we can do is we can also determine the amount of each phase. So let's pick a different color here, dark green. So let's say we're at this temperature here, and we want to know the amount of alpha phase and the amount of liquid phase. Okay, so we've got the place where it crosses the liquidus, we have the place where it crosses our composition, and then we have the place where it crosses the solidus. We're going to call this, let's call this, I don't know, let's call this little L1, and then we call this distance little L2. Okay, so we got these two parts of the tie line. Then the fraction of liquid is going to be the inverse. So that point is touching the liquid. So we take L2 divided by the total length of the tie line, L1 plus L2. So you see that? We take the place where it touches the liquid, we go to the opposite side, that's L2, and then divided by L1 plus L2, and that tells us the fraction of liquid. If we want to say the fraction of alpha, well, alpha, that's where it touches the solidus, so we take L1 and divided by the total length, L1 plus L2. And that's how we determine the fraction of alpha. And right now that may just sound like it's some recipe, but it actually does make sense, because if you think about it, let me draw a real quick diagram here. So as I'm going liquid alpha plus liquid alpha, A, B. Okay, so as I'm going from liquid and I first cross into my two-phase region, well, as I first cross in, that means it's going to be mostly liquid. So that means that this part is longer, right? This is the fraction. So that's going to be get a better pen here, something's a little sharper. L1, L2. So now, if I want to know the amount of liquid, that's going to be L1 over L1 plus L2 equals fraction liquid. And now let's say I keep cooling down. Now I'm right at the edge of the solidus, right here. Well, now, if I want to figure out how much is present, I draw this line. And we know that we're really close to the solid line, which means it's mostly solid. So now, L2 and L1, the fraction solid, is going to be L2 divided by L1 plus L2. So the rule is that the liquid touches the tie line on this end, therefore you take the opposite part of the tie line. Here it touches the solid, therefore you take the opposite to know the amount of solid. And you can think of it that way. Another way to think of it is to actually just look at it and say, well, I'm coming into here, there's more liquid because I just crossed the liquidus, therefore I take the long part. And that's another way of thinking of it. And that's how we read a phase diagram. And we'll work some example problems to see how to work with this. But first, though, I want to continue talking and show you some more phase diagrams that have a little bit increased complexity. So the next simplest, or the next most complex diagram would be what's called a binary eutectic. Phase diagram. So a binary eutectic phase diagram will look like this. So this is A, that's B, that's XB. This is temperature. And this is what our phase diagram will look like. We have liquid at a high temperature. Over here, on the A side, we have a solid, and that solid we're going to call alpha. It's a solid solution which is mostly A and a little bit of B. Over on the B side, we have another solid solution which is mostly B and a little bit of A. I'll call beta. We know that if you have a single phase, you have a binary phase diagram, and you have a region with single phase and another region with single phase, then between them you have to have a two-phase region, alpha plus L. Same thing here, beta plus L. And then here we have alpha and beta, which means in here we must have alpha plus beta. And this is what a eutectic phase diagram looks like. We still have the solidus, where the first solid forms. Sorry, liquidus. L-I-Q-U-I-D-U. Liquidus. And we still have a solidus. But now we have this, where we're going from beta into a alpha plus beta, and this is called a solidus line. And then this point, E, this is a eutectic point. And what's interesting about that is that the eutectic, or I should say anything along this line, if you have a temperature, and this temperature is called the eutectic isotherm, but anywhere along this temperature between these compositions, you pick a spot there, you're going to have alpha, beta, and liquid present. So anywhere along here, you're going to have three phases that coexist. In contrast, anywhere here, you're going to have two phases. You have alpha plus liquid. Here, alpha plus liquid. But that makes something that makes the eutectic special. So let's look at some cooling paths, right? So say we start up here in liquid, we cool down, we now start forming alpha. So at this point, we have a system which is made up of alpha plus liquid. And now we come to this, and at this point we have alpha, liquid, and beta coexisting. And then just as you cross in, you now have alpha and beta only. And we'll look at the microstructure and how that transforms later in this lecture, or later in this chapter. But nonetheless, that's what happens when you cool. Now, over here, we have something different. Here we start out in liquid. We cool down. We now have alpha plus liquid. Keep cooling. Well, that liquid went away at that point at the solidus, and now we have pure alpha. And then if we keep going, here at the solidus, we now have beta forming, and here we have alpha plus beta. And this is how we read these phase diagrams. So we can take and do exactly the same thing we did before in terms of reading the composition. So let's say I'm at this point, and I want to say, okay, so what is the fraction of alpha versus fraction of liquid? Well, I draw my tie line. I then measure these distances. So this is going to be L1, L2, and I can say at this point, fraction of alpha is equal to, look, cross the alpha there, so it's going to be L2 divided by L1 plus L2, and then the fraction of liquid, well, the liquid's on this side, so I'm going to take L1 and divide it by L1 plus L2, and that gives me the fraction of each. And then I can say, okay, what's the composition? Well, the composition of the liquid is where my tie line touches the liquid, or the liquidus. Drop that down. That is XB liquid. And then the composition of my alpha phase is where I touch the solidus and draw that down here. And that is XB alpha. And this is the binary eutectic phase diagram. So let's talk about what happens when we have an intermediate phase. So right now we've just talked about A and B. But what if we have A, we have B, but these also make an intermediate compound, AB. We'll make a 1-to-1 molar ratio. Well, that means that we'll have something that looks like A, B, then AB. And that's what we draw in. And let's say that it is a line compound. So a line compound is a compound that doesn't form solid solutions. So basically they're going to be a straight line. So when I had this binary eutectic, I had beta, which was a solid solution of B and A. If I had a line compound eutectic, it would look something like this. L, A, B, A plus B, B plus L, A plus L, right? And we don't have that broadening where we have an alpha. And if we talk about these as line compounds, one thing we could have is we could have something that looks like this. So here we have A plus AB. Here we have AB plus B, liquid. This is liquid plus B. This is liquid plus A. And this is liquid plus AB, B. So I should probably just take that out, like that. And this would be a set of line compounds, A, B, AB. This is B, temperature. And that's how we can work with these. Phase diagrams get incredibly complicated because you can imagine as you start looking at real materials, you're going to find A, B, A2, B, A, B2, A2, B3, and you're going to have all sorts of line compounds around here. But this is kind of the simplest intermediate compound phase diagram we can have. And we can take that and we can add some complexity to it by adding a solid solution. So if this had a solid solution to it, what that would basically do is that would take this area and it would broaden it out. It would take this and broaden it out, and it would broaden that out. Right? So we'd have something that looks like this. A, AB, B, now let's make this that. Like that. Okay, so we still have liquid. Now we have A with an alpha solid solution, B with a beta phase solid solution, AB, let's call that gamma. So that's another solid solution. We have gamma liquid, which means here we have liquid plus gamma, gamma liquid, again, liquid plus gamma. Here we have beta and liquid, beta plus liquid. Here we have gamma and beta. So here we have gamma plus beta, alpha liquid, alpha plus liquid, alpha gamma, gamma plus alpha. And this would be a phase diagram. Again, it has an intermediate compound, AB, but instead of being a line compound, it has a solid solution. And this is the structure that type of phase diagram would have. So you can see the difference between line compounds, which have very thin, well-defined stoichiometric definitions, and we write them as their stoichiometric compounds compared to solid solutions. Kind of an interesting point about this type of phase diagram is this point is actually kind of special, because if you're down in here and you go up into liquid, it goes straight from gamma into liquid, right? There was no two-phase region in there. And that's called a congruent melting point. Or congruent freezing if you're going liquid into gamma. And that's a special point in phase diagrams. So this is one thing you can do with an intermediate phase, but we can do other things as well. So let's look at again A, B, B. If you draw this up, we can have our line compounds again. And one thing that can happen is we can have something that does say this. So here we get AB plus B. Here's liquid. We get L plus B. L plus AB. Here's a eutectic, and it's worth pointing out here that this diagram we looked at before, there's two eutectic compositions and two eutectic isotherms here as well. And this is, again, another eutectic here, E. So now, on this side, we could do something different. And what we're going to do is we're going to draw this straight over, and this like that. So now we have A and AB, so we have A plus AB. We have A and liquid, so A plus L. And we have this kind of interesting little place that has to overlap. Right? We have to have overlap here. Because otherwise we would have A and liquid. So if this doesn't overlap, then we have a region of A and liquid, or I should say solid, A plus AB and liquid in contact. So this overhang is what's keeping the phase diagram valid, and that comes from rules of thermodynamics, which we're not going to cover in this class. But the interesting thing about it is that now, let's say you're up here and you cool down. Okay, so now you're in A plus liquid. And now as you come down here, you're now in L plus AB. So what just happened was that A phase, which existed here, was completely reabsorbed, and AB comes out. And this, what's happening there, is called a paratectic reaction. L plus A going to AB there. So again, this is B and temperature. And that's a paratectic phase diagram. And again, if we wanted to, we could take this and we could make this into a material with a solid solution. By saying A, B, A. So we take and we basically broaden out these. So let's try to draw this proportionally, huh? There. So now we have an alpha, a beta, a gamma, alpha and liquid, alpha plus liquid, alpha and gamma, alpha plus gamma, gamma and beta, gamma plus beta, gamma and liquid, gamma plus liquid, beta and liquid, beta plus liquid. And this would be a paratectic phase diagram in which you have solid solutions of alpha, beta, and gamma. So you have this intermediate phase, which is the AB.